Okay, in this video we're going to look at a kind of a review of interpreting graphs on the AP Calculus test. So it says the graph of the function f shown above consists of two line segments. Let g be the function given by this. Now the first thing I would do with this right here, this integral, is list the other relationships I know. I'm going to do that right up here. G of x says is equal to the integral from 0 to x of f of t dt. Well, if g of x is equal to the integral, then g prime must be equal to just the function. See, I just took the derivative of both sides, and fundamental theorem of calculus part 1 says you take the derivative of an integral, you get the function out. So let's continue though. G double prime is equal to f prime. So I'm just using kind of the algebraic idea. I'm doing something to both sides. Then I go to my kind of key where it says what I'm looking at, and I say, okay, they've given me the graph of f, but really they've given me the graph of g prime because g prime is equal to f. And I make that distinction right away that I have been given the graph of the derivative of g. Okay, so part A, it says find g of negative 1. Well, g of negative 1, I'm going to write this up here, g of negative 1 is the area from 0 to negative 1 of the function. Okay, it's an area collector. Well, the area here, we have a triangle 1 by 3, so 3 times 1 divided by 2. The area is 3 halves. But because we're really working backwards here, right, our bounds are backwards, it will be negative 3 halves. Even though it was positive area, it'll be negative 3 halves because our bounds are working backwards. Okay, so that's g of negative 1. Well, g prime of negative 1, and again, go over to your kind of blue key here. You know, we're just substituting g of negative 1. We put negative 1 there. G prime of negative 1 is equal to f of negative 1. Well, f of negative 1, we have the graph of f. F of negative 1 is 0. It's just the graph's value at negative 1. And finally, g double prime of negative 1 equals f prime of negative 1. Well, derivatives mean slope. So what I'm looking for is the slope of this line, or the slope at negative 1. So you look at this and you say, well, it went up 6 units in the course of 2 units, so the slope is 3. So there we have g of negative 1, g prime of negative 1, and g double prime of negative 1. Next, for what values on the open interval is the graph increasing? Well, something is increasing, g is increasing, when its derivative is positive. We have the derivative. Remember that. We have the derivative. So it's from negative 1 to positive 1. And we've really done both things here. It says for what values and explain your reasoning. We've done that. It's from negative 1 to 1, and my reasoning is that's where g prime is greater than 0. For what values is the graph concave down? Well, concave down, you could justify 2 ways. You could say that the second derivative is negative, but a better justification then would be to say that g prime is decreasing. And I say better because we've been given the graph of g prime, so this is a better explanation because it's using the graph we've been given. So when is g prime decreasing? Well, it's decreasing all the way from 0 to 2. So that will be our interval. Okay, I'm going to answer these bottom 3 on the next slide. Okay, now a local maximum. Well, local maximums occur when the derivative changes, g prime changes from positive to negative. Okay, well, where does that happen? It happens at x equals 1. Of course, a minimum would be the opposite. G prime changes from negative to positive. Inflection points. Inflection points occur when the second derivative changes direction or signs. I'm going to write that here. Changes signs. But a better justification, because it's based on the graph we have, is that G prime changes direction. And that occurs at 0. It does not matter that this graph is not differentiable at 0, because this is the derivative of G. So G has an inflection point because G prime changes direction. G double prime wouldn't exist at 0 because of this corner, but it would still change signs there. Okay. All right, finally, the absolute maximum. Well, remember, I'm going to do this one up top here because it's going to take a little more work. Maximums occur at critical points or endpoints. Okay, so here's what we need to check. We'd need to check -2. We'd need to check -1. We'd need to check 1, and we need to check 2. Now you'll notice I said absolute maximum, so I'm going to put a little dot here because -1 you wouldn't actually need to check because it's a local minimum. So you can't be an absolute maximum and a local minimum. I'm going to check all of them because you may be asked to do an absolute minimum, so it would be good practice, but you would not. You wouldn't need to check it in this case. Now by check, I mean we should actually get the function's value. So I'm going to use this g of x, okay, and I'm going to basically plug in the x values. Okay, so x, -2, and so on. So let me do this. Let's find out these areas because, of course, g relies on the integral. Okay, so we already had said that this was 3/2 and this was 3/2. And if you'll notice that this is then -3/2, and of course this is the same. This is -3/2, it's below the axis. So at -2, if you think about, you're doing 0, because that's the bottom bound, the total area here, you've got 1.5 negative units of area and 1.5 positive units of area. They cancel each other out.